Hello, everybody. I'm Dr. Shafiq, and I'd like to welcome all of you in this video session. Today, we'll review lateral earth pressure. Okay. Let me share my screen with you. So you can see here is a retaining wall along that line, which has a height of h. And if this retaining wall is straight, didn't move this way or that way, then basically we call that one at rest, like condition. And the soil, the horizontal pressure or the lateral pressure of the soil on this wall, we call that one at rest pressure. Now think about, like, because of that pressure, there is a chance that this wall will move a little bit this way, outer side. Here, this one has moved a little bit here. It's a very small movement. So in that situation, what will happen? Let's say this soil wedge, this one will fail along that line, and this soil here will try to rest on this inclined wall. Remember that this actually distance is very, very small. Actually, you don't see that one sometimes in your naked eyes. So what will happen at that situation? The active pressure, or the pressure that's coming from here, will be a little bit different than your at rest condition. So this condition, like when your wall moves outward, then basically we call that one active situation. On the other hand, in this figure, you can see, like, because of the movement of any traffic or something, let's say this is a wall or abutment along a bridge, and then actually, like, traffic is moving this direction, which will try to move this wall inward to the soil wedge. So that will try to create a crack in that line, and you will see at this time we are calling that one like the passive state, and the pressure from the soil to the wall, we call that one passive pressure. Okay, so horizontal pressure could be three different situations: at rest, active, and passive, based on whether your wall is still there or it's moving inward or outward of the soil. Okay, so based on that, actually your pressure will vary. So you can see here, this is like your pressure, at rest pressure, and this is your active pressure. Active pressure is usually lower than your at rest pressure, and your passive pressure is usually much higher than your pressure at rest. Okay, so now we'll just talk about each of them separately, and we'll just include, like, what are the situations you are going to face at the field level. Okay, so there are two methods to find out the lateral soil pressure. One is Rankine's method, the other one is Coulomb's method. The difference between this method is Rankine method assumes that there is no friction between the soil and the wall. It's just wall is very frictionless. On the other hand, the Coulomb's method assumes that there is friction with the soil and the wall. Okay, so at the same time, this Coulomb's method is only applicable when this retained soil here is granular soil, means like sandy soil. That's the most common thing happen, like when we build a wall and then fill that one with soil. So we usually fill that one with granular filler. But many times you will see that if there is already soil there, and then you have to now construct a retaining wall, in that situation, basically, you can have your CFE soil there. Okay, But usual case, you have to fill that one, then basically we fill that one with granular soil. Now, what are the different situation, or what are the different things that could, like differ in the field case? First of all, slope of the soil top. It could be either 0 or alpha slope. We are talking about the slope here. When the soil slope is flat, means like alpha equal to 0, we call that one flat slope. And if there is an angle here with the slope, we call that one inclined slope. Okay. And now, second thing is wall geometry. Like the wall could be something like that, a cantilever, or that could be a old gravity type or semi-gravity type wall, which has a back face. We call that one back face. That back face could be either vertical, or that could be with an angle. So based on that, actually your pressure will also change. Now, fill material. Okay, so what kind of fill material we are going to use here? So basically, you can use either granular material, means like your sandy soil, or sometimes you can use like CFE soil, which means like which is kind of like a mixture of sand and clay. Okay. Now, Rankine's earth pressure. First, we are talking about Rankine earth pressure, then we'll be talking about the Coulomb's earth pressure. Okay. So the most common situation we see that when there is no slope here, okay, and the back face here is vertical. Okay, this is a cantilever wall, vertical, and this soil could be either granular field or CFE soil, but there is no slope here. In that situation, the Rankine's at rest pressure would be, the horizontal pressure would be equal to K naught sigma prime. You already know that your sigma overburden or effective stress is equal to gamma H. H is the height of the wall. And your K naught, which is called the at rest pressure coefficient, which is usually 1 minus sine phi prime. Okay. Now, if this wall moves a little bit outward this way, then basically this one will be active condition, means like there's a wedge here that will fail, and you will see that actually the pressure here will decrease a little bit because your wall has moved a little bit this way. Okay. So in that situation, for CFE soil, your active pressure is equal to Ka, means like the coefficient for active earth pressure, sigma O prime, minus 2C prime root Ka. And if this soil is granular soil, then you understand that C would be 0. So basically your active pressure would be Ka sigma naught prime. Okay, where sigma naught prime is gamma H and Ka equal to 10 square 45 minus P by 2. In your actual, like video, like actual lecture, you can see we tried to develop that equation, that how did you get like Ka equal 10 square 45 minus P by 2. I'm not gonna discuss that one, everything here in this review session, okay? But just trying to give you the synopsis, like what you need to remember that one at this moment, okay? Here is your passive pressure. Your passive pressure is K naught Kp sigma naught prime plus 2C root over Kp, okay? And once again, you can see if this is granular soil, then your C prime would be 0. So basically, your passive pressure would be Kp multiplied by effective overburden pressure, which is equal to gamma H. Now, again, here, your Kp is 10 squared 45 plus Phi by 2. We explained that one to your original, lecture notes, that how you can find out your Kp and how we got that 110 squared 45 plus Phi by 2. So just try to remember that one, so that if your soil doesn't have any slope and this is back phase is 90 degree, then you can directly use this small equation to find out your lateral pressure. Now, sometimes things may be a little bit complicated, that you have soil which has an angle of alpha, then you have a back face which is not 90 degree, let's say, which is making 30 degree with the vertical, and you, for this case, like this is the back, in that situation, actually your equation would be a little bit different for granular backfill and CFE soil. So here we are just talking about if you have granular backfill, okay? So this is the general equation for your sigma A. And then you can see, you can find out your psi from that equation, your active force, which is basically half gamma H squared Ka, and Ka is the active pressure coefficient. The value of Ka can be found from table 6.1, or you can use this equation to find that one. So I gave you the spreadsheet, like to find out your Ka. So if you know all these values here, like your theta and your alpha and your phi, then basically you will be fine. Just plug that value there and you will get your Ka value from there, okay? And the active force direction, that how this one will, which direction this one will be working. So you can see this is your actually back face. This is the perpendicular line here. Okay, so this is the perpendicular to this line here. Okay, and this is the angle beta. This one will be working at like beta degree with your perpendicular line. Okay, so this one is basically your beta. The value of beta prime can be find out from table 16.2 in your book. Okay, now let's see that what happened, like the very same thing, but your face is vertical now. Like this is just a special case of granular backfill. If you just fill that one, your theta equal to 0, this means actually this one will be this one here, okay? Now in that situation, actually, oh, this one is actually basically for CFE soil, okay? For CFE soil. So you can see for CFE soil, you don't have any solution when this one has a angle, your back face has an angle, okay? But if you don't have any angle, means like it's 90 degree, then basically we have a solution. In that situation, your active pressure would be gamma Z Ka cosine Ka prime cosine alpha, while your Ka prime is this equation, okay? And the value of Ka prime can be found from your table 16.4. I also gave you the information in the spreadsheet. So if you change that, plug that value C prime, your gamma, and change your Z, then basically you will find out your Ka prime. You can see your Ka prime here is actually a function of your Z, which is not like very kind of unique, because in any other Ka equation, we never use like Z, because it doesn't change with Z. Here, this one, this Ka changes with your Z, means like with your height, okay? So if you plug those values in the spreadsheet I gave you, or use this equation, you can find out your Ka prime. You can also find that out directly from your table 16.4, but sometimes you will see that the table is using only like some, like numbers at a regular fashion, so that your phi and let's say your alpha, these are changing only like from 5, 10, 15, 20, something like that. But if your alpha is 7.5, maybe you cannot use that table directly, but definitely you can interpolate the values and find out the values from there, okay? Now, vertical wall backface with granular backfill. That's actually, we are talking about now the passive pressure. Okay, now we are talking about the passive pressure. So vertical wall backface with granular backfill. So this one you can see, this is your vertical wall, and this is a granular soil. This one has alpha here. And you can see this is your passive pressure is actually wall is creating pressure towards the soil. That's why soil is reacting. Okay. Why this wall is trying to create pressure to the soil? Because of the movement of the wall towards the soil. Okay. Because of some external forces or something like traffic forces is more common, is mostly common. Okay. So you can see for passive pressure, Rankine's passive pressure, this is your equation. Kp is this one. So Kp is basically your passive pressure coefficient. Okay, so the value of Ka can be found from table 16.9, or you can use this equation directly to calculate what would be your Kp. Once you get your Kp, you can find out your Pp, means like the passive force, which is half into gamma h squared Kp, and passive force direction, always parallel to the topsoil, means like alpha degree with the horizontal. You can see this is alpha degree with the horizontal. Same thing is true for actually active case, that this PA should be always parallel to this angle here. Okay. Now vertical wall backface with CP soil. Okay, the other one was granular soil. Now we are talking with CP soil. So you can see the passive pressure is gamma ZKP prime cosine alpha. And you can see here that actually this one is a little bit different in the equation we have been using. Okay, very similar, only you will see that for active case and passive case, actually this signs has changed. Okay, this value you can find out from table 1610, or you can use this equation directly to find out your passive pressure, like coefficient. This one is also included in your spreadsheet. So if you change some of the value there, you can get directly your Kp prime from there too. Okay. Once you get your passive pressure, then basically your passive force would be half into gamma h squared Kp. Okay. And what about the passive force direction? It's always parallel to the topsoil, means like alpha with the horizontal. So it doesn't matter whether this is CP soil or granular soil. The direction and the passive force equation is same, only this equation is different for granular soil and CP soil. Okay. Now let's talk about Coulomb's method. So you understand that Coulomb's method is a little bit different because Coulomb's assume that there is friction between the soil and the wall. Okay. So in that situation, the generalized case for granular backfill, one more time, Coulomb's method cannot be applied for CP soil. It's only for granular soil, not CP soil, not clay soil. Okay, your Coulomb's method cannot be used for clay soil or a mixture of clay and sand soil. It's only for granular backfill. Okay, now you can see here your active pressure sigma A is again K active multiplied by your overburden, effective overburden pressure, which is equal to gamma H. And you can find out your Ka from that equation here, but the value of Ka can also be found from your table 16.6. And also you can find out your Ka from the spreadsheet that I provided to you. Okay, this equation is there. If you add this beta value and phi prime, then basically this one will calculate your Ka from there. So in that situation, if you look at the figure here, Beta is the angle here. Angle of the back face with the horizontal, that's beta. Angle of the back face with the vertical, that's actually theta. Okay, we use the theta for Rankine's pressure. For Coulomb's pressure, actually, we use the angle with the horizontal, which is beta here. Okay, once you get your active pressure, then you can find out your active force, which is equal to half into gamma h squared Ka. And what about the direction of the active force? Makes an angle delta prime with the perpendicular line to the back face. That's actually common for all Coulomb's method. What is that angle? This angle is like, look at this back face here. This is the perpendicular line here. Okay, this is the horizontal line, this one. And this is the perpendicular line with that surface here. So your active pressure, Coulomb's active pressure, always makes delta prime angle with this perpendicular line. Okay, so that's your passive pressure. That's your active pressure, Coulomb's active pressure, which is making delta prime with the perpendicular line. Okay. Now, let's take a look for Coulomb's passive pressure. Okay. Actually, Coulomb doesn't have that many cases here. This only like 2 different cases, like generalized cases for this one, granular backfill for active pressure, and generalized case for granular backfill for passive pressure. Okay, so you can see this is your equation for your Kp. If you look at your Ka, only difference is like some of the, not, like signs has changed. Here is positive. If you go here, then you can see it's negative. Similarly, if you see there is positive, this one has changed negative. It's a very similar equation, but the signs are a little different. So once again, you can get this value directly from this equation or the spreadsheet I provided you. You can just plug those values like beta, phi prime, delta prime, and then basically you can get your Kp from there. Once you get your passive pressure, you can find out your passive force from this equation and your passive force direction, which is very similar to your active pressure, like direction, that it makes, like delta prime angle with the perpendicular line of the back face of the wall. Okay, the only thing is your active pressure is under that line here. Your passive pressure is above that line here. Otherwise, everything remains same. Okay. I just added some of the problems here, example problems here, which is basically the same example problem that I added in your regular lecture. So try to listen that one so that you can understand what is the solution for these problems. Okay. So basically, I'll stop it here. And if you have any question, please feel free to ask me. Okay. Send an email or something. Okay. Thank you so much. I appreciate that.